The next talk is by Sujit Ravi from Google, and he will talk about on-device machine learning with neural projections. At a high level, this talk probably will tell us how to make our smartwatches even smarter.
I can't promise anything, but how's everyone doing? Hopefully caffeinated and ready to hear more. Yes? Great. I'm Sujit. I'm a research scientist in Google Research, and I lead a machine learning team that focuses on large-scale machine learning, specifically related to how do you do graph-based machine learning and how do you do graph-based machine learning plus deep networks at scale. So obviously this talk is not about doing stuff on scale and on the cloud, but more on on-device machine intelligence applications. So part of my team actually works on how do you take these machine intelligence applications that we can power, by making predictions on the cloud, and how do you fit that on device? So I'm pretty excited because I think we're at the juncture for both from a research point of view and also from an industry point of view that both algorithmically and innovations in hardware are coming to sort of like a nice little intersection where we can actually make some of these things work really well in practice. And more importantly, we should start thinking about new ideas on how do we develop more efficient machine learning techniques in general, right? So it's not all about, making things faster, but if you can make the same model give you the same quality at 1/100th of the size or at 1/100th of the compute, that is not just making you do things faster, it's also enabling you to do 10 times more things or 100 times more things. So the talk itself is going to be structured as follows. First, I'll tell you about machine intelligence applications and what we use them on the cloud, kind of some of the marquee features you've heard from Google over the last couple of years. Then I'll talk about how do you do this for on-device applications, right? Specifically, I don't need to beat home the point why on-device machine learning is actually important. You've heard that already, but I'll give you some motivations for us why this is an important area. And what are the challenges? And finally, the most interesting part of the talk, the technical aspect, would be this new idea of learning fast and tiny models using projections. And this applies not just to deep neural networks, but other ML areas as well. And lastly, given the backdrop of this new idea that I will introduce, I would also like to talk about model predictably, because this is something that we sort of ignore, right? We train our best deep networks, we get the best performance, but we typically don't say, how good is actually this network? Can it be made better? And I'm not just talking about quality. What is the quantitative measure of the predictability of this network? Can you quantify that in terms of something more principle, traditionally information theoretic bounds and things like that? Okay. So by the way, feel free to ask questions at any point. This is supposed to be an informal session, so the better and the more questions you ask, the more interactive it'll be, and also it'll be more interesting for us as well. Let me just keep track of the time. Okay. So first of all, deep networks have come a long way. If you haven't already noticed, just look at the size of this conference, compare it to the size of the conference last year, compare it to the previous year. We are exponentially growing, and I have no idea how NIPS is going to handle the conference this year. Many of you know what I'm talking about. But primarily, there are a lot of areas that these applications or networks have actually been able to deliver very good performance, and computer vision being one of them. We have networks that can actually look at images and understand what is in them, for applications as diverse as handwriting recognition. So you have stroke sequences and you recognize characters, or you have more complex tasks like image recognition, what are objects inside the images, right? So, but what do we actually use them for? At Google, we have several applications that we've built using state-of-the-art machine intelligence, and one of them is this semantic visual understanding. So how many of you have felt like that, you take hundreds or thousands of pictures, but when you want to share that, one photo that you're okay, I was at that beach, or I was at the Sydney Opera House, let me share that. Now you have to start scrolling through your photo gallery, right? I mean, you have no idea how to find that. So with machine intelligence and better computer vision, we can actually do this already. We have technology in Google Photos that allows you to search by semantic concepts. So if you're a person like me, I love dessert, I can search for dessert and it'll pull up pictures from, this is from a trip from Rio, and it shows me only the items or like gallery pictures that are very relevant to that concept. Now this looks like magic now, or this looks like, hey, this should already be available on every phone right now. But a few years back, this was not the case. This is all possible because of deep neural networks. So the idea is like, take hard problems, build complex models at scale, solve them, and make the models more and more efficient. This is not limited to vision alone. You heard a lot of talks about computer vision, but language understanding is a very important area for us. This is also a focus for my group, both image and language understanding. And so we have neural networks that can read and understand text these days. So machine translation is a holy grail application for natural language processing. So we have neural machine translation systems that have achieved now very good accuracy and quality, surpassing the old phrase-based translation systems. So you have some source sentence and you're in English, and your goal is to translate into a target language. And we have systems that can now do this in multiple languages, even though it's not been trained on that language pair. So this is all possible because of these neural machine translation systems. On the flip side, there's another class of problems which involve semantic understanding. That means if I give you a word or a sentence, I want to understand what the semantic intent or representation of that word is. So if I say awesome, you know what that means. It's a good thing. If I say ROTFL without telling you what that acronym stands for, probably if you use it in chat, you know that means funny. But how do you learn this automatically from text? So machines are pretty dumb, right? I mean, you need to teach them how to do this, but without hand-holding. So we have networks that can do this as well. Where they're used is to power conversation understanding applications. You saw Alexa mentioned we have something called Google Home, if you know about that. And a lot of the applications involve dialogue understanding. How do you look at conversations and understanding what are users saying? And this is not just for Google Assistant, but also for your messaging applications. Show of hands, how many of you know or have heard of Smart Reply? Okay, a few of you. For those of you who don't know, in 2015, we released a feature called Smart Reply, which is basically a machine learning system that looks at incoming email messages and automatically suggests short responses that you can answer. That means if you get a message like, want to hang out, it'll show you suggestions like, yes, I'd love to, or maybe later. So the interesting part is this is actually suggesting very diverse responses. So it's not like saying thank you or okay or like all the time. It actually suggests very good quality responses. And this is done completely by a machine. And there was a time when we thought that we would never ever release this feature because this was like in research and we were like, okay, this sounds cute. But we were pretty amazed over the few months that we spent developing this. The machine started understanding very subtle intents, like response intents, like even nuances. Sometimes it would understand humor. Like it would read some text and it'll say, haha, that's funny. So I don't have a good example to show, but there are like in the blog and other places we've actually mentioned this. So this was a feature called Smart Reply. We first released it for email and then later for chat applications. And under the hood, there are a lot of things going on for Smart Reply. I'll break it down for you a little bit. But in general, the goal is like all these applications are doing something interesting, and the way they work, in a nutshell, is this, right? You pick your favorite machine learning model, and these days it's obviously deep networks. And you do some learning on the cloud, you use GPUs, CPUs, your favorite, whatever you get your hands on, like distributed systems. Do the training, you push your model, and once the model is frozen, you just query it for predictions. And this all happens in the cloud. This is true for all the applications that I just showed you. Let's take an example, the Smart Reply application that I showed you. How do you now take an application like Smart Reply, right, which involves all these complex concepts? So in the learning stage, what Smart Reply does is a number of things. So it's not just taking a vanilla deep network and training it on some chat conversations. Because if you do that, the most likely responses you're going to get are thank you, thank you, thank you, ... exclamation, comma, all kinds of variants of that. Unsurprising because that's what most of chat conversations are all about. So to make it work and actually understand semantic intents in conversations, so we combine graph-based machine learning and deep networks like LSTMs and some other types of neural networks. If you're interested in this, there's a KDD paper from last year which breaks it down into like different components. Also, if you're interested in this general idea of how do you combine structured prediction or structured learning in the realm of graphs in a joint fashion with neural networks, there's a talk tomorrow at the Deep Structured Prediction Workshop. I would encourage you to check it out. It's the last talk of the last session of the last day of the conference, so it should be exciting. So if not anything, we'll have some fun there. So, okay, so this is how Smart Reply works. A lot of complex things going on, graph learning, machine learning, using deep networks, how do you combine them effectively? There are different types of neural networks used as well. But once trained, you have this LSTM model that now takes an incoming message like, hey, how's it going? And then generates predictions. Like, I'm doing okay, great, thumbs up. So, of course, yes, we said chat conversation, so it can predict emojis as well. And any guesses as to what's the most common emoji in chat? I have to ask this question. Which one? The poop emoji. So, as I said, when you're training networks on data, just be careful. I mean, if you just blindly train them, obviously the distributions of classes or intents manifested by users is what your machine is going to pick up. So you have to do some more smarter things to actually make it work and be usable. Okay, so this is how Smart Reply works. Now everybody knows you can get predictions by querying this trained model. But one of the questions that we were asked were, can you actually do this from your watch directly, right? I mean, so on the inference side, if you give a message, do you actually have to send it to the cloud? Can I build a Smart Reply model directly on my smartwatch? Of course, the usability and like the advantages are pretty obvious. I'll state a few in a few slides, but this was like an interesting question for us because the models we were using were like, quite large, these LSTM models. It gives very rich predictions, but they're like, I can't tell you the exact size, but they're like several hundreds of millions of parameters. In general, the question becomes, can you do this on device for any type of application? So for inference, if you're given an input, if you have your favorite model, how do you fit it on your device? And the device could be anything from a watch to your phone, or other in and enough things like sensors and stuff like that. Now, there are several reasons why you would want to do that. For us specifically, this is probably kind of a set of different reasons than already mentioned. The obvious ones are you want low power, etc. But connectivity is a big issue. If you have, let's say, a messaging application which uses SMS, or let's say an application that looks at images and makes some prediction, and suddenly you run out of Wi-Fi, or you're like in a no Wi-Fi zone, and your model stops predicting something. Was that a good experience? Obviously not, right? So you can't obviously expect to send all the information all the time to the cloud to get predictions. So this is one of the reasons why you'd want to do predictions on device. Secondly, privacy. If you're using models or data specific to a user and the user doesn't want that data to be sent to the cloud all the time, then you'd actually have to make these applications and features work directly on device. So that's a big reason to do this. And there are different techniques to do this, like privacy-preserving machine learning. I mean, this is a very active field now, and there's a lot of interesting work going on there. And finally, efficiency. So if you have models that are generating same type of predictions, you'd actually want to use it, and make it applicable for multiple applications. So if you have an image prediction model, you don't want to take 10 models for 10 different apps and put it on the device, right? I mean, you'd want one model that all the developers can actually access. So there are some nice qualities that you would expect in any on-device. Yes. Yes.
Do these actually apply for this email smart response thing? If you don't have connectivity, how do you get your email numbers?
Oh, so yeah, good question. So the question was, does this apply to Smart Reply? In the Smart Reply case specifically, it is for messages. So your SMS messages that you get, right? Or your messaging app you're using, Hangouts or anything like that, right? For instance, you don't actually need Wi-Fi sometimes. You can actually get the messages through SMS and to make make some predictions. Email, obviously, if you don't have Wi-Fi, it'd be very hard to get email, right? So it doesn't matter if you can make or don't make predictions on them. But the idea is generally that connectivity should not be a bottleneck for making predictions, right? Especially powering applications. Probably this is more true for vision, right? I mean, if you're doing something interesting for pictures that you're taking on the fly or on the go, you probably don't want it to stop working when you're like, in this remote forest somewhere in the middle of nowhere. So some of the nice qualities about this, you want from a requirements point of view, like the inference should be low latency, like it should be really fast, the memory should be small, data should remain on device, nothing too surprising, you've already heard this. But how about this? I mean, like for the rest of the talk, I'm going to break it down into like 2 specific questions, right? Now, if you want to do on-device machine learning, how do you choose what models and what the architecture should look like? In particular, do you really need huge networks to make this good performance, right? I mean, the size and complexity of these networks have a trade-off with the prediction quality. How do you choose that optimal point? This poses a lot of machine learning challenges. Like if you actually want to run these on devices, I mean, in addition to all the things that you've already heard, like hardware is obviously a constraint, but what about quality? You can actually shrink models and make them work, but if it is at the cost of the experience, for instance, if you take a 100-way classification problem and say, no, I'm not going to predict over 100 classes, I'm only going to predict over 10 classes. That simplifies the problem a lot. But that's not useful, right? In the case of smart reply, instead of predicting over the rich output space, you say, I'm just going to show you 3 responses all the time. The same, okay, yes, maybe. It might work, but it's not the same experience. Secondly, the modeling architectures, as I told you, like you can combine these different types of complex systems like graph learning, deep networks, all like working in tandem, in concert on the cloud very easily. But if you have to do that on the device, there's no easy way to do it, right? I mean, each of them have their own quirks, and now making them work together on this small device is going to be even more challenging. The problem accentuates as you go to more and more complex settings. Like, for instance, if you're doing structured prediction instead of simple classification, or if you have high-dimensional spaces or large output spaces, it's becoming like significantly more challenging. This applies to the cloud as well, but at compute and memory constraints in devices, the problem is like exponentially harder. So there are several techniques for doing machine learning on devices, compression, etc. I won't enumerate all of them for obvious lack of time. And you heard some of the techniques already mentioned by Forrest in the first talk. But there's some other, even older techniques like dictionary encoding, and there's a whole field of compressed sensing. And typically, let me break it down. Most of the compression work to date has been like heavily focused on you have a trained model. Now, I fix the weights, how do I make them work on small devices? So you do quantization, you do compression, like, reduce floating point operations from 32-bit to 16-bit to 8-bit. Can you go lower? Okay, that reduces the memory footprint. There are a host of other techniques that people do, like feature hashing. That means, you project the spaces of input features into much smaller dimensions, or like random edge removal. You start randomly pruning things from your network. Distillation is like a very common technique, not necessarily just for small networks, but for other areas as well. I'll come to that later and why that's actually great. And then how do you learn things like by sharing weights? For instance, if your network always predicts minus 0.3, 0.2, and 0.1, I mean, I should actually share the representation of this rather than replicating them like 10 times for every node that is activated in the network, right? So these are all techniques, but the one common thing with many of them are the performance degrades as you go to high-dimensional data. If your vocabulary size increases, that means like if you're doing some language prediction task or the task becomes more complex, the performance significantly drops. So this is like the backdrop for all the work that we've been doing on how to do fast and like tiny on-device models that can actually make efficient predictions and at quality levels that are like pretty good, that's usable. That means like the user doesn't actually perceive there's a difference between on-device and cloud models. So earlier this year, we released a smart reply model or feature that sits directly on your Android smartwatch. So if you have an Android smartwatch, you can enable smart reply for any messaging app that's, like whether it's WhatsApp or Telegram or Kakao or whatever your favorite thing is, and get predictions from that model. And so how do we do this? Like at the core, the idea is we learn fast and efficient operations that sort of simulate these tiny networks. In the process, we are getting compression factors of more than 100 to 1,000 times. There's a paper, if you search by ProjectionNet, an early version of this paper, so in the coming weeks it will be updated. This is what I'll be talking about, but there are also many other techniques that are covered in this talk, which we hope to roll out like over the next few months. Okay, so how do you learn these efficient networks? And one of the core ideas we'll be using throughout this talk is this idea of neural projections. And the steps are pretty simple. I mean, this is all work that algorithms people have been doing for a long time. The question is how you use it in the context of deep networks or other machine learning models to make it more efficient and trainable. So the 3 steps in the process, one is projection. So we basically define a set of operations, which we call projection operations, which transform some input or some intermediate representation, this could be a hidden layer in a network, into a set of nodes or like representations. And this is what we'll call the projection model. So a projection model is nothing but a set of operations that you apply to any layer in the network. The key property of this, it should be fast and efficient to compute, because that's what we are aiming for. Okay, now that you have defined a projection model, we train a projection model with a trainer model. This is similar to the teacher-student kind of network that you might have seen. And both of them are jointly trained. So unlike distillation, we're not fixing the trainer and then training the projection to simulate it. Both of them are jointly trained. The key is, like, for the trainer, it can be as large as possible. The training will happen on the cloud. There is a setting where the projection model itself will start adapting on the device. I won't be talking about that. If you're interested, ask me later. But joint training is important, and I'll show you why that is important. And once you train the projection model, inference happens on device. The model is tiny. We persist on the device, and you get an input. You apply the same set of projection operations, and you get some predictions out. Okay, so the key questions: how do you train this projection model? For the trainer itself, it's pretty flexible. We could use deep neural networks. That if you do that, and then you have a neural network type architecture in the projection model, then you get like a projection net. There are other types of mechanisms you can use as well. So because of the flexibility, you can take any of your favorite models, like a LSTM model or a CNN or a feedforward, or even things like graph-based machine learning models, and actually train these projection operations. And that's key because some of them are more suited for scenarios like semi-supervised learning or structured learning. Or you can combine and mix and match these. So for the trainer perspective, it doesn't matter. Depends on the task. And you want to actually choose the best model for the task that you have. So let's take an example of projection net that uses feed-forward networks. So the key property, as I said, is this joint training over both the networks. So the loss function is defined as a combined loss function over 2 or 3 different components. Rather than looking at the equations, I'll save you the trouble. I'll just show you a picture of that. So here's what happens. So if you take a feed-forward network, let me see, okay, if you can see this, so the top half just represents a regular feed-forward network. And we call this the trainer network. And what it does is takes an input, applies a set of operations through the hidden layers, and gives you like a prediction. One of the loss functions is a classic neural network loss, defined over how different are my predictions from the true classes. You do the same thing for a projection network. You take the same input, apply a set of projection operations, which results in some representations. And the key is what these representations are. But after that, you apply some activations, you get a different set of predictions. There's a loss that compares the projections output to the ground truth, and also compares the projections output to the predictions from the trainer network. And the reason is that why you want these 3 losses, each of them behave very differently. If you just train a projection network blindly on the ground truth, the representation power might not be that sufficient to actually incorporate all the information there. Whereas the trainer can actually simulate the full distribution if it has enough complexity for a given task, it can actually generate a much richer distribution. So the projection can actually learn much better from that. So this is like, now if you replace this with a CNN or an LSTM, you get like an LSTM version of the projection net. So there are some key aspects of how you represent this projection net, right? I mean, so what are the operations that you saw in the previous slide? I mean, what is this thing here, right? So essentially, it's a way of transforming some inputs, and we basically parameterize this as like t different functions. So for any input or any input layer, we apply t different functions to that layer and generate some representations. Each of those t functions generate a d-dimensional vector. So the complexity is t times d. So how do you do this? The key is these are pre-computed, and each of them, as I said, gives you a d-dimensional vector. But you shouldn't spend too much time or too much compute in making these projection operations work, right? So that's the key. So how do you do this? There are several ways to apply projection functions, right? I mean, you could do SVD, you could do embedding matrix lookup, etc. In our case, what we found was really useful was computing these using a modified version of locality sensitive hashing. So in a nutshell, so how many of you are familiar with locality sensitive hashing? Okay, so basically it's a way of projecting similar input representations into nearby points in some metric. So basically, if I show you this example, I'll show you this one and then go back to how we do it. If you have all these messages, howdy, everything going well, hey, how's it going? How's it going, buddy? All these to us look very similar, but they are in high dimensional spaces because these are over words or character sequences which have a much larger vocabulary space. But if you have a projection operation that can actually convert this representation into some vectors, that means that things that are nearby in the space all represent things that are semantically similar. That's a good projection operation. Whereas something like that's funny is far away because it encodes very different type of features. So this is essentially what locality sensitive hashing will give you. I'm obviously glossing over a lot of detail, but there's a nice theorem from Charikar long back that shows you that if you have two vectors, the angle between the two vectors is basically proportional to the signs that any random vector applied to these two vectors will match. In other words, if the angle is wider, then these two after projection will actually appear very far apart in the projected space. If the angle is closer, they appear very nearby. So that's essentially the property that we're exploiting. So similar inputs will be projected into nearby projection vectors. And these vectors are now in bit space. That means you have zeros and ones. Everyone with me so far? Yes?
You keep saying the input is high-dimensional. What is high-dimensional for you?
Oh, so like for instance, in the case of language prediction, it's a sentence. And the vocabulary of the words in the vocabulary would be anywhere from hundreds of thousands to millions.
So you're using a bag of words representation rather than embedding?
Yes, because the key is that this is, I think, exactly here. If you were to use embeddings or pre-trained embeddings, now you have to store these embedding matrices. There are ways to get around that by saying that, okay, I will only store embedding matrices for characters, and then I'll figure out how to combine them into words later. But all of them, in our experience, has been explodes the footprint considerably, whereas in the case of these projection operations, you can actually dynamically compute them on the fly. That means the P functions applied, all they require are very small set of parameters, sometimes just 10 or 20 parameters. And when applied to the input feature space, they will automatically generate the projection vectors that I showed you. We don't have to store the entire projection matrix ever in memory. They're think of them as something analogous to hash functions computed on the fly. Some details like the memory size is t times d, but it can be reduced to t further. But the reason for showing you t different functions are, you could think of during the training process, I'm applying t different projection functions, each of them generating some sort of representations. The training is basically trying to figure out, for this given task, which of those operations are actually useful for me. So that's the weights that you're learning. And so once trained, then you can actually filter out the ones that are not important and then use the remaining for predictions.
So what prediction matrices do you use? Are they topic
Sorry?
What are your projection matrices?
Yeah, so the projections would be, let's say you have a simple like one layer projection network, right? The input layer is in some high dimension space. You can apply LSH. You will, with T times D, you will just generate T times D bit vectors.
Yeah, so the LSH projection matrix is typically a random or topological.
Yes, it's a random.
So you need to store that.
Yeah, so the key is you don't store the entire the vector which is in the dimensionality of the feature space. You actually just store T random numbers. And you use the column ID of the feature and the actual value, dynamically compute a new value. This will apply to that and generate 0 or 1 based on the sign of that the vector. So just to break it down, you don't store the entire projection matrix in memory. You're basically storing some random numbers, and you use each of those random numbers with this function to generate a value that'll then get generated and activate that neuron in that particular layer. So, and you can stack them up. So basically that means you can stack them to get deeper versions of projection networks. So you have a projection layer, you have other layers like a CNN or fully connected and more projection layers, etc.
Wouldn't that hurt the guarantees of the LSH?
Yes, so there is some, exactly. So the question is, wouldn't that hurt the guarantees of LSH? Yes. The key is you want to use the weights, the intermediate layers. In the input layer, it doesn't matter because that's fixed, right? You're not changing them. As you go higher up, you actually, there are a couple of things. You want to make the projection layers also differentiable. So rather than zeros and ones, you actually want to apply a different type of function. You can still compute the, whether the dot product of the two vectors. But rather than saying 0, using the sign activation, you might want to use a different function. That'll allow the network to trickle the gradients down much faster. Otherwise, what happens is, like, if you take gradient of derivative of a constant at 0, you're not learning anything interesting, right? And note that here the goal is not to be biasing the intermediate layers or the input layers to learn similar representation, but the goal is not to preserve the approximation guarantees. The goal is to say, okay, preserve it up to the point where you can actually make better predictions. So the bounds will be slightly different compared to traditional dimensionality reduction.
Sorry, I didn't understand this fully because I can't see your slide. Are you saying that rather than storing the random projection matrix, you're just going to store the random seed and then use that to generate the matrix?
Yes.
So then you're just trading off RAM for CD.
Wait, not necessarily, right? So because for each value, I mean, the number of operations that are required would be T times D, right? And T and D are sufficiently small enough that actually you don't incur too much penalty. I mean, these are like of the order of 10s or 20 or something like that. And the D.
It depends on the architecture, right? Depending on if you have a random number generator, how expensive that is.
Oh, yes. So things like, for instance, I mean, you don't really need a random number generator that is like, there's actually preserving randomness. So like you can take any pseudo random number generator. Now some of them actually give you much better collision rates or better collision or worse collision depending on what you use. In the case of this, the goal is not to actually generate like the perfect random number. We just want to simulate that process, right? I mean, technically you could take, instead of doing random number, you can just take the ID of like, the number and just concatenate them and just do some mod operation, then you can actually generate the similar kind of result. And we have tried such experiments. So the randomness here is basically not the key aspect, is basically how do you compute given some fixed representations into some like low dimensional representation, but do this dynamically and very fast. I mean, you're absolutely right that depending on the complexity, most of the architectures actually have very fast random number generators by now, like your phones or even watches, which we piggyback on. So we don't use anything fancy to actually make this work. So here's, okay, once you train this, how does this work? This is how inference works. Like you actually have a fixed, okay, question? So let me go back. Okay, you see this one, right? So this defines what are the operations that I mentioned earlier generate, right? Like intermediate representations. But these edges are actually weights that you're learning during the process of training. So there are obviously some weights. So when I quantify how the size is going to be represented, I'm just going to talk about parameters, because compression can be applied to regardless of the trainer or the baseline projection network. You can compress them, quantize them the same way. So once trained, the network is fixed. You have these functions that are, with the seed that I talked about, that basically encodes and defines what are the operations that you're going to apply to an input that generates some predictions. So the activation is, like, depending on classification or whatever, it's like a softmax, for instance. Let's see how it does for some tasks, like visual recognition and language prediction. And this is, by the way, very recent results, like evolving as we speak. But if you take like MNIST or some classification task, like 10-way classification, and we use a baseline network that's like 3 layers and with some 1,000 units per layer, we can use this as a trainer and then train different versions of the projection network that are at different size granularities. So what we notice is, and before I go on, this is without convolutions, and like for image classification, everybody knows we need convolution, so this is permutation invariant. So what we notice is a tiny projection network, like almost like 400 times smaller, gets like more than 90% accuracy. And on MNIST, this may not be that surprising, but the key idea here is that like you can shrink the models, and this is like, or rather the word to use is you can train a small model to simulate the performance of the large model at very high accuracies. And a couple of things we noticed is like, if you take this projection operations and stack them up, that means you go deeper with projections, you can actually improve the performance. So with just 2 layers, you can actually almost get to the performance of the baseline network. And this is at like orders of magnitude lower in size, so like almost 15 times smaller. And the other aspect I'd like to point out is joint training helps. So somebody asked, like, why does it matter which losses you use? So if you just train the projection network alone on the ground truth, it does not have enough parameters, right? I mean, because obviously the size is small, it does not have enough parameters to actually learn from the ground truth, because the ground truth, it's, especially for classification, it's spiked at some one class, right? Whereas when you're training in a distillation kind of manner against the trainer and the ground truth in a combined fashion, you're actually now also trying to mimic the full distribution that is generated by the trainer network, which is much richer. So we've noticed like significant improvements in performance by doing the joint training. So somebody, I think Forrest asked this question, like, why does distillation work? So we've, in our experiments at least, we have noticed that this actually helps quite a bit, yes?
So is this just basically sort of piggybacking on the gradients from the big model to search in the space of the lesser model? Is that
Yes, I mean, in a sense, yes. So you could do things like just as with like older distillation methods, just freeze that trainer network, don't change that at all. Then what you're going to do is you're basically looking at the distributions generated from the trainer, right? I mean, so rather than saying that here's a 10-bit vector and this is the class at 5, position 5, I'm going to get a probability distribution over all the classes, and that's what I'm going to simulate over right now, or train against. So if the trainer is fixed, that's what's happening. But you can actually train the trainer and the projection simultaneously. There's a couple of reasons to do that, and this matters more when you have less amount of data, because trainers, as they grow in complexity, can tend to overfit. So if you train them against a smaller model, they tend to regularize much better. So in some cases, we've actually noticed that doing this joint training helps the trainer's performance as well.
So for
Yeah.
what's your model size?
So when I say t equal to 60, d equal to 12, that means 720 parameters. So basically 720 bits, that's the model representation. Does that make sense? So the baseline is like a 3-layer network that's about, I think, 2.8 million or something like that. I mean, you can obviously reduce it further and further. For MNIST, it's not a big deal, right? It's a simple task. All these models at the bottom are in the order of either several hundreds or early thousand. So the compression ratios are shown here. Like, I mean, you get, let's say you could get up to 80% performance with like a compression of 2000 or something like that. But more parameters you add, we actually notice a better increase in performance at high compression values. So you could do the same thing, take a small network with the same architecture, fewer layers and fewer neurons, and what we notice is the compression ratio that you achieve at the same performance level is much higher for these projection architectures than like a regular neural network architecture. Here's some results on the CFAR task, but again, this is just for the purpose of showing against a baseline network, how does it do? This is, I would say, useless because this doesn't use convolutions, but the idea is to show like if you take a baseline model that gets, let's say, 60% performance precision at 5, which is not that great, you can compress it and get like up to 45% precision at like a factor of 45x or 50x or something like that, smaller. And you can go, the more complex this network, you can, or the more layers that you stack on projection, that compression ratio can actually increase. Because there are ways to improve the projection layers and the fully connected instead of removing, adding a fully connected, you can do things like pruning and like the techniques that Forrest mentioned. So those are all orthogonal to this approach that I'm talking about. So you can do all that like quantization and everything else and train, compress like the Songhan kind of method on top of what I just described. The improvements are actually more significant for language, and there's a reason for that because we are in high-dimensional spaces. As I said, you're operating over words and sequences. If you take a baseline network that's an LSTM, and we train a small version of the smart reply task, a very miniature version where we are trying to classify between 20 different intents given an input message. We take a 2-layer LSTM, and with 100 dimensions, we get like close to 97% precision. It's almost perfect, right? Now, you can get more than 80% of this performance just from training a projection net with 700 odd parameters. So this is like several millions of parameters versus just hundreds of parameters. So that's the compression that you can actually get. Okay, so just a quick word on what is this useful for? So one is obviously compression, but I think because we are now operating in this bit space, you can actually do some very interesting things. I told you the projection is now generating bit space, right? Basically bit vectors. You can use the generated bits to quantify how good your original model was. That means if you take a projection network trained against a given model, like a feed-forward network with 3 layers or something, and you compare the performance of the two, you can now say, I can quantify this original model using X number of bits. And so this is what this plot shows. So like for MNIST, it says that just 100 bits are enough to recover almost 85% of the performance. And like 700 bits are enough to get more than 90% of the performance back. So I think there's some interesting thing here, not just for on-device models. We should be able to quantify our networks much better. So there's a sort of tendency to mix and match all kinds of architectures without, experimentally validating them. But what if we can actually now theoretically say, okay, if I give you a network, okay, here's the model capacity or representation power in terms of like some information theoretic metric. That would be quite interesting. Now you can use that to actually now start training better models, coming up with alternate representations. So I think there's a lot of work to be done in this direction as well. This idea is obviously not limited to the deep networks. I told you that you can take the trainer and replace it with something else. You can use graph-based machine learning to do this. I won't go into details. That gives you a projection graph. The paper covers some of the details. Instead of networks, now you have projection graphs and trainer graphs, and you're defining some sort of joint loss function over both of them. So in smart reply, it's a combination of everything. So you have messages and projections, and you have messages and their responses. We train both of them, which generates a learned prediction model. And essentially, the projections is like simulating this specifically. So similar input messages get projected into similar spaces. And if one of the responses is good enough for any message in this bucket, it's good enough for all the messages in this bucket. So you can now start like collecting and basically learning richer responses in low-dimensional spaces like this. So this is already in Android aware, so you can easily access this, be published to blog, but there's an easy API that you can actually plug any of your favorite app into to get the predictions. But to summarize, I mean, I think we all understand that on-device machine learning is interesting and important. It might also be useful to think about what are the theoretical and research implications. So should we think about like better and more efficient techniques, generalizable algorithms that not only apply to on-device settings, right, but it also helps us think about efficient models on the cloud as well. Because compute is not free. Like your watch is definitely way slower than some machine on the cloud, right? So obviously these will all get better and better, but that means if it gets better, can I do more with less? That's the idea. And I introduced this neural projection idea and also how it can be extended to other scenarios. Something that is very exciting for us, and I don't know how many of you know this, we announced at Google I/O this year, we're going to be releasing a new library called TF Lite. So this is not, we'll incorporate some of the ideas I described here, but essentially it's a custom runtime library built from scratch, highly optimized for on-device applications like deep network inference. And we'll be releasing it soon in open source. So we're pretty excited about this. So stay tuned to get information about that. Essentially, if you have TensorFlow models, you should be able to run inference for your models out of the box. And it'll also support hardware acceleration and other sweet things. So with that, thank you for your time. And happy to take questions if you have time.
So we are really short on time, so maybe one question and then we can ask Sujit questions later during the day.
I'm wondering, so your smart reply model has a wide list of replies. You select a good reply of the wide list. How well would an on-device prediction work for an unconstrained language-related model?
So the question was like, smart reply is actually predicting over a constrained space. So in the case of smart reply, we learn what the rich set of responses, the constraints should be offline, and then we now constrain the LSTM to predict one of those responses. In the on-device setting, we have a new version coming out which will actually adapt basically to new responses automatically. So you have a model that'll be trained, and then it'll actually adapt on device to new responses that is never seen before.
So we'll take all other questions later.